To further clarify your queries or concerns, so I have decided to create this video lecture in such a way that I would give an example that would be related to your exam. So given the function f is equal to not a plus b and not c. So if you were given a certain function, so you need to generate the truth table as well as the schematic for this function. You also need to implement it using Electric and verify the output through Winspice. So first, you need to generate the truth table. So you will assign A as your MSB and eventually C as your LSB. So this would be your most significant bit and this would be your least significant bit. So you have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So this is 0, 1, 2, 3, 4, 5, 6, 7 in decimal value. So you're going to use this function. So this is the given. So if A is 0 and not A, or to B and not C, automatically if your A is 0, you will have a high output across your F. Then the only way B and not C will become 1, since their logic function is AND, B should be 1 and C is 0. So B is 1 and C is 0. So which has a value of 6. So the remaining inputs should have an output of 0. So another way of generating the truth table is by using Excel. So you can use Excel file. So you can assign A, B, C, and F. So 0, 1, 0, 1, 0, 1, 0, 1. Then for B, 0, 0, 1, 1, 0, 0, 1, 1. Then last, 1, 2, 3, 4. For the function, since our function is not A plus B and not C, so that would be equal to our function not A and B and not C. So if the answer is true, so that is 1. The answer is false, that is 0. Thus, we end up with 1, 1, 1, 1. So that 0, 0, 1, 0. So that would be a digit, or that would have a value of 0, 1, 2, 3, and 6. So same with the first generation of truth table. So either you manually generate the truth table or use Excel. As long as you use the original equation, you should end up with the same value. So you could also try both and verify if it would match the same, it would give you the same answer. So to solve this problem, next step is to convert the given equation. So use the Morgan theorem. So you need to apply it on this equation. So all functions with OR will be converted to AND. So A and with B, C. Since we have two variables across this bar, so you can further divide it since they are uh, using AND, it should be converted to OR. Then if you have double bar, that would be cancelled out. So A ANDed with not B and C. So to further simplify, you have A ANDed with not B or C. So that would be the function that you should implement in your uh, standard static CMOS design. So we always start with the pull down network. So as you have watched on the video lectures, you actually have a pull up network consisting of NMOS, and you have pull down network consisting of your NMOS. So if you're going to implement that using standard CMOS design, so we need to invert the function, since if you're going to use standard CMOS design, it is naturally inverted. So you need to apply De Morgan's theorem, just like what we implemented here. So for the pull down network, so A is ANDed to B or C. So that would be A ANDed with not B and C. So for the pull up network, obviously we cannot use the same connection if the given is in parallel, which you connect it in series and vice versa. So as to prevent both pull up network and pull down network connected to supply and ground at the same time. So at a given time, it should only be connected to the supply or to the ground. So either pull up network is off, pull down network is on, or the other way around. So thus we have your A connected to a series connection of B. So A, not B, and C. So this will be your function. This is your supply. This will be your ground. For the sizing, so always use 2:1 ratio. So if that's the case, since we have uh, two items here, so if you want to have 0.8, we should have a size of 1.6 micro for transistor A, 1.6 micro for transistor B, and also 1.6 micro for transistor C. Since this is 2:1, so this should be 1.6 for transistor A. Transistor B is 3.2 micro and C is 3.2 micro. So kindly use the procedure that I have given in computing the transistor size. So if you're already familiar with it, so you can easily compute the given or the required transistor sizes for these transistors. So I already have created the circuit for this one.
So as you can see, input A, so this transistor on your left and this transistor on top. So similar with the one that we have designed. So left on of the pull-up network and up on the pull-down network. B and C on the pull-up network is in series, and on the pull-down network it is in parallel. So since we need inverted value of B, we introduce an inverter after the input B. So this is our input B, then this is our inverter. So connected to this transistor as well as the transistor on your pull down network. As for the pulse, since C is our least significant bit, we're going to use 50 and 100. Always use 50 and 100 as your lowest value. Then always double this value on the succeeding input up to your most significant bit. So C, your least significant bit, so the value of B, you are to double this 2, so that would be 100, 200. So for B, that is 100, 200, and for A, that would be 200 and 400. Okay, 200 and 400. If you need another input, for example, you were given a 4-input problem, then your most significant bit should have a value of 400 and 800. As for the transient, so since the highest period is 400, you only need one cycle for that. So assign the highest value for your period. So in this case, 400. Since we just want to determine if we will have the correct function, just use 1 nano. So we can have a bigger step size since we only want to determine if we would get the same result as our from our truth table to this circuit. So again, assign C as your least significant bit, starting with 50 nano and 100 nano as your period. Then increase it, double it, up to you reach your most significant bit. If you need an inverter across your input, so just add an inverter depending on your derived equation. So let us now try to simulate this circuit. We should arrive with the one that we have on our truth table. So tools, simulation interface, write spice deck. So let us use sample test.cir. All files.cir, save. Yes. Okay. Then open it with Winspice. File, open. So you will notice that all plots are on top with one another. So for you to arrange it, so the topmost part should be the most significant bit, and the lowermost part is your output. For you to be able to do that, use the command plot, start with the output VF, then since our supply is 3.3, use greater value for your step size, So you can use 4. So VC plus 4, then just double it or add 4 for every other input. So VB plus 8 and VA plus 12. So enter. You will notice that we have this as our output. From our truth table, we should have a high value across if our input is 0, 1, 2, and 3, as well as 6. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and 1, 1, 0. So let us go back to our simulation results. So 0, 0, 0, so high, 0, 0, 1, 0, 1, 0, 0, 1, 1. So 0 to 3, we have high input. So this one would be 4, 5, 6, so 1, 1, 0. So we also have a high value. So thus, we were able to generate the correct function, as well as we're able to properly get or assign the transistor size for each and every transistors. For your exam, again, you need to generate the truth table. So always use the original equation for your truth table. Then just use De Morgan's theorem for you to develop your circuit. So once you were able to simulate it, your output should be the same as your truth table from the original function. So you need to submit the screenshot for your output, the .cir file, as well as the electric library. So I hope this would help you in your exam. So good luck, everyone.